Today I will be talking about coconut. It will be a two-part talk where in the first half I'll introduce coconut and the motivation behind why we have developed this and the challenges that we are facing at the moment. And then we will gradually transition into markers, which is a AI-powered literature extraction tool that we are currently and also plan to use this going forward in order to improve the quality and also the quantity of the coconut natural products there. Okay, to begin with, let's quickly check with natural products. So as you all might have known, natural products are a really rich source of information about biological activities and also the defense signals and various aspects of the life sciences which are actively used in development of new pharmaceutical drugs and also pesticides and a few other things. They are quite critical, and any source of natural product information is super valuable in drug discovery and associated sciences there. So to touch upon what's the motivation behind developing Coconut as a database back in 2021, as a part of Christoph Steinbeck's research interests, we are primarily motivated in understanding natural products, and we have been trying to develop various cheminformatic tools such as the NP likeness scorer, where we would like to understand the differences between synthetic molecules and natural products, and also score molecules based on their likeliness hood there. So as a part of this, we have tried to accumulate or curate all the natural products that are available and available only in the open space, and then realized that there are diverse databases that are spread across different domains, but there is no single source of information which is reliable and also standardized using one single pipeline. So that has led to the development of a database called Coconut, which is what we are discussing about right now. And it has a collection of around 63 individual natural product sources, which are all in open source domain. And then we published this paper back in 2021, which had around 500,000 compounds in there. But before we actually developed the database, we did understand the situation right now that there are multiple databases. Do we really want to develop one more database? And why do we want to develop one more database? Can't we just use them as such? And this is very clear, nicely illustrated in the demonstration here, where, of course, there is always a need for developing another database. We are not happy with whatever that's already there. And the reason behind this is there are a bunch of challenges that we have come across when we try to unify data across these databases. First thing is a lot of databases or some of the largest databases of natural products are primarily not open. They are not available for us to use. They are under the paid walls. Either they are available only for the big pharma companies. It is not commonly available for anyone to be able to quickly search and then use that. And also they have varying reliability. You might find a database accessible today, but down the line in a few months' time, it is not guaranteed that the database is available anymore, or the links where you have referenced previously a natural product might still not be available a few days from now. And also we have observed this innate discrepancy with the natural products that are curated out there is that since most of the databases are in a way accumulated from other natural product sources, an issue in one natural product source can filter through and then eventually end up in another natural product collection. And then eventually there is this recursive imports of these natural products across different collections there. And also the data sometimes can be inaccurate, there can be duplicates, and also there can be missing information. So I'll talk more about the fine print there in the next few slides. So back in 2024, we have also revamped the entire infrastructure of Coconut and published a new version of the Coconut database, Coconut 2.0, where we have accumulated data from over 63 sources, and then also published a standardized pipeline based on Campbell curation pipeline. And we have also enabled a lot of fair related features, which made sure that the data that is currently published on Coconut is all available, accessible, and also reusable for anyone to use there. So, what does actually Coconut store? So, yeah, you might find it in the slide here. So, Coconut doesn't have all the analytical data or the bioactivity data, but what we are primarily focused is on the natural product structural information. So you have an accurate description of the structure. If there is stereochemistry available, then we have the definitions available. And for each and every structure, you have the sources of information, if it is a collection or if it is also cited in any publication that are out there, all this information is available. And wherever there is possibility of obtaining an organism information, we have that information, and also the organism names are all standardized. You find an IRI associated with organisms pointing to a taxonomy, a classification. And also in some cases, you might also find the organism part to which the extraction of the natural product has happened. And the geolocation of the compounds are also available on certain collections, which we also standardize and distribute the data. There is other metadata associated with the compounds, which include cross-references to other databases and resources. We do not store any biological activity information or any analytical spectra, such as NMR or mass spec. Instead, we directly point the users to those corresponding resources, which are also currently being developed as a part of NFDFK. So how are we doing in terms of the numbers? So if you look at the slide here, we are a little over under 700,000 molecules right now. And then the collection space has increased from 64 to 70 recently, and we have around 70,000 odd unique organisms that are annotated here. And also the compounds natural product source information is mapped to around 120,000 citations. You might have already realized that these organism information is not just written as a string text, but we also map it to a standard NCBI or any other relevant taxonomic classification. And also the citations are all associated with the DOIs of the publication where this is originally reported. And one interesting stat here is that you might find on the bottom right corner of the screen the revoked molecules. So this is in relation with the active curation that is happening on the database. So we have removed around 40,000 compounds, which are reported by our users and also found by ourselves with sufficient scientific evidence that they are not natural products or could be a synthetic derivative of a drug or a solvent that are potentially used in the process of extraction. So whenever there is a report or information that a compound that is on natural or on coconut that is not a natural product, we revoke those molecules, and you should be able to see the scientific evidence and the reason why this has been revoked there. So, as I mentioned, Coconut is an aggregate of around 64 collections originally, and now has been extended to a little over 70 collections, and there are a few collections that are in the pipeline. Each and every collection, we want to attribute the original authors or the creators of the database. So every collection that has been imported into Coconut will get its own dedicated collection page. And we also issue a DOI, a standardized identifier with all the metadata associated with the collection automatically populated there. But we also export the imported collections in the form of STF. So if anyone wants to just download that single collection and be able to process this, you should be able to do that. And these individual collections are also redistributed based on the original license that the authors have been distributing on. Here is an example of a Coconut collections page where you should be able to browse around different collections, search, filter, and also be able to explore the details of the individual collections there. So coming to the actual workflow or the pipeline through which we standardize these compound information, we built the coconut curation pipeline based on Campbell curation pipeline, which is based on RDKit. And what we do is we take the original source information or the annotations from the individual collections and we pass it through the Campbell curation pipeline. We check for any structural errors. If there are no severe errors, then we filter those molecules and then import them into Coconut. We do standardize a lot of metadata there and then compare it to the existing data on Coconut, and then we accumulate all the data into one single schema that Coconut is following. And there are several ways you can submit the data to Coconut. One is you can submit the compound collection through comma separated value files, which is a lot more human friendly. Or you can also use the web interface to submit new compounds. Alternatively, you can use the REST API in order to submit compounds or report any issues with the existing data through programmatic way. And also there is a nice way of exporting and importing data through large language models, which is what the second half is going to dig into. I'm not going to go into the details of every step in the curation pipeline, but if you are interested, this is very well documented and also available on our documentation page. And happy to discuss if you have more questions there. Moving on, as I have emphasized previously, one of the key important feature that we would like to introduce through Coconut, which is lacking in the community, is the community curation. Um, there are several databases out there, but typically they suffer the big issue of being outdated, and also whenever there is non-natural product being included as a part of the collection, it's never easy to report the original authors except through emails about the issue associated with the compounds and also the metadata associated with that. So one of the primary reason why we have developed Coconut is to enable this community curation where individuals can report non-natural products or synthetic compounds on Coconut and also suggest or request changes to metadata associated with the compounds. And also we wanted to build a platform where we would introduce or leverage the large language models to help us improve the quality of the data and control this submission process either semi-automatically or automatically to a certain extent through agents that are powered by the larger language models there. And another key feature of the curation interface is the audit trail. So every change that we or any users do on Coconut, it be whatever the fine print there, everything is audit trailed. So you should be able to dig into the details of when this has been edited, who has edited it, what has been changed, and when this has been changed. So you can complete the audit trail of every change that has been happening on the database, which is quite critical. So you can understand and follow the trends in how evolution of these natural product research and also curation has been happening over the years. Here is a couple of screenshots of how reporting and also requesting changes to Coconut entries can happen. So on the right hand side, you should be able to see if you have a particular compound that you have evidence that it's not a natural product, you should be able to fill in a few details and be able to submit it. And one of the curators will approve it behind the scenes and it should revoke the molecule and with the right reasoning behind it and also evidence reported on the page itself. So you should still be able to access the compound information on Coconut. It's not taken away from the public interface, but you still see a reason why this has been revoked and that it has been revoked on so and so date. On the left-hand side, you see the requested changes from the users where they should be able to change every fine detail that is associated with the compounds except all the auto-calculated properties. But if there are any structural changes, then when structural changes are reported, our curators approve it, and when it is accepted, then a pipeline kicks in and then it automatically changes this. Although changing structural information is not straightforward, we wanted to still keep control over what changes happens and when who approves it and things like that. So if you would like to explore and when you explore Coconut, On every compound page on the right hand side, you should be able to see this report this compound or request changes to this page on every page of the entries that are there on Coconut. And then users should be able to report this. We also do a bit of analysis on the data that we have, which is quite critical in order to understand the quality of the data. So we have a dedicated statistics page where you should be able to dig into the details of the chemistry and also other physicochemical properties of the natural products that are out there, which we also actively use in order to filter compounds and then curate them semi-automatically on a regular basis. Here are some of the statistics that we display. We also do classify the compounds using NP classifier and also classifier. All this information is readily accessible for anyone to explore a bit more on our statistics page. Moving on, if you would like to curate your own collection, you should be able to do that. Anyone should be able to create a new collection in Coconut and then upload their own set of natural products. And once you start doing this, you should be able to share links to these collections or the individual pages with filters applied and also all other typical features that you would normally expect on a well curated interface of any software there. Um, Moving on, one of the important features that Coconut offers is also the way you could export. Not only you can export these individual collections as shown in the previous slide, but you should be able to export the entirety of Coconut in the form of HDFs, both 1D, 2D and 3D structures, but also you should be able to export the entire database itself in its original format. You can also export a comma separated values of the entire data set. We have a lightweight version and also a full download that is available on the Coconut exports page. Even though the database is live, so the changes happen on a regular basis, we do a monthly exports for softwares and other tools in order to be able to do the imports on a regular basis. Everything is timestamped, so if you do a research on the exports, then you can refer to the exact version of the Coconut export that you are using in order to do your analysis and infer. Yeah, not only that, we do export data, metadata that we analyze and export. So in this case, we offer fragment exports, which are primarily derived from the Motor tool that is developed in-house by Jonas from our group. And also we export tool-specific export formats as and when we have requests from our users. In this case, Compound Discoverer in mass spec has a dedicated export from our downloads page where you should be able to import the file into your tool and be able to do mass spec related analysis there. If you are tech savvy and would like to interact with Coconut programmatically, you should be able to do that. We have a standard open API specifications compliant API or REST API that we offer. Not only we do allow users to query, browse, or filter or search the Coconut database, but you should be able to dig into the fine print and be able to extract individual compound specific information. Although you need to have the appropriate rights and permissions in order to delete or do any actions that are a bit more critical there. Soon we will be also be exposing a MCP server associated with Coconut, so you can have your LLMs also interact with Coconut on the go without having to export the data and import there and then use it. A bit more technical information. It's all built on open source. It's MIT licensed, Coconut, and for those that are interested in the cheminformatics aspects of this, we use Postgres database behind the scenes, and we have an RDKit cartridge for Postgres that is used in order to do the compound searches and also the similarity or substructure searches there. And we do have an internally developed microservice called cheminformatics microservice, where microservice allows us to interact with the standard toolkits through one unified interface. It's a bit out of scope to dig into the details there, but if you are a cheminformatician and would like to work with any of these toolkits or would like to reuse any of the components that we have developed, cheminformatics microservice is a good place to start with. There is a dedicated publication if you want to explore more into the details there. Again, this is all microservice-based architecture, so you can deploy this on any infrastructure in just few commands. So we also have Helm charts if you would like to deploy it on a Kubernetes cluster. This is all well documented on our documentation site if you want to explore a bit more into the details. So again, it's all MIT licensed. In case if you would like to access the code base, you should be able to explore the GitHub page of Coconut and all the um, active development that is happening in Coconut is also visible through the issues where we actively update as and when we have new issues reported or new features that are requested and developed. So where do we stand at the moment? Although Coconut has a little under 690,000 compounds, but what we realize is that there are a lot of natural products that are still that needs to be explored. They are hidden, unliberated in the literature, in papers, and also the data that is currently on Coconut doesn't have full coverage in terms of the citation references and the organism associations. So if you see in the graph on the bottom right-hand corner, you see a little over 40% of the molecules on coconut has direct references to the organisms where these compounds has been identified. So we are constantly working in order to improve these associations to prove that every compound on coconut has association to an organism backed by a citation information where this association has been reported. So this is something that we are actively working on. And also every organism that is reported needs to be associated with a taxonomic reference. We just don't want to report a bunch of string values there. So that brings us to the second half of this talk where the information is there in the literature. This is a typical expert from a journal, a natural products journal, where you have information in the text and the associated structural information in the tables or the graphical representation here. What we are interested in is extracting chemical names and associated with the chemical names, the structural information that is in the infographics. And then you also have the chemical classes information, then the organism names, and also organism parts in certain cases, and the biological activity, and also the geographical location. So typically, this information is all hidden in the literature, and we would like to automatically or semi-automatically extract this information from the literature. And then this is where we're gonna introduce Marcus. So I would like to hand it over to Kohulan now.
Thank you, Chandu. So, I will start from where Chandu has left. So it's basically chemical structures and text extraction. One of the things which we look into is chemical depictions, and extracting them into a machine readable format is called optical chemical structure recognition. When we initially started, the work is mostly done by rule-based tools. The rule-based tools follow these 7 guidelines or principles: scanning, vectorization, searching for dashed bonds, and character recognition, graph compilation, and post-processing. So when you go through these sort of rules, sometimes it may fail, and you won't get the chemical structure exactly as it is, how the author depicted in his publication. In order to overcome this, what we try to do is we try to develop a tool which basically uses deep learning and computer vision to extract the chemical structure as it is from the printed literature. Decima has 2 components. One of the component is, say, identification and segmentation. So what it does, it goes through a printed publication like this, detects all the chemical structure. Each individual chemical structure is identified and segmented into an image. The second part is it takes the image and tries to predict that into a smiles format, where we can use the smiles format to later convert that into a mol file or so on and so forth. The whole project is known as Decima. So as I said, Decima has 2 parts: segmentation and the image converter. The segmentation, if you look into it, you can send a publication like this. each publication gets transformed into an image, and then we use the image to work on later. First of all, it will detect and segment out the chemical structures like this, and there is a cleaning up process where it takes these images and gives you a complete black and white images as chemical graphs. This paper is already published and the tool is already available on GitHub, and it can be easily installable. Currently, this is the only open source software which does this detection and segmentation. Second part is the image transformer, where we trained a model using 450 million synthetically generated chemical structures, completely trained on Google TPUs. And currently this model also available in our pipeline called Decima.ai, where it takes any publication or a single image like this and converts that into a machine readable format. One could easily use the machine converted image to edit or download as it is and use it in their pipeline if they need to. This work also has been already published, and the Decima AI platform is available for everyone to use. And the GitHub profile also holds the Decima.ai code as well as Decima image transformer Python package. So if somebody wants to do mass mining, they can simply download the Decima image transformer and run it on their laptops. One of the things which we focused in the last year is how to improve Decima apart from printed literature. Two things which crossed our minds was how to convert a hand-drawn chemical structure into a machine-readable format, which will be in theory useful for ELNs when they become more popular and more used. And the second thing is how to get the coordinates exactly as it is from the printed structure. So these two models being worked on. The hand-on chemical structure model is already online, and the coordinates is being developed and will be available soon. One of the things which we notice while we are developing these OCSR tools, there are quite a lot of open OCSR versions available. Not all work well on a given benchmark dataset. So on average, if you see Decima works well, but still there's a long way to go. But this is the case for almost every OCSR tool. And also all these benchmarks were done on patent data sets, not on journal articles. What we later did was we looked into the current open OCSR tools. There are quite some have very high performance. One is MolScribe from the MIT team, MolGrapher from IBM Research Zurich, and MolNextar from University in China. All these three does exhibit very competitive performance, where MolScribe and MolNextar is being very easy to install as well. So MolGrapher, we tried to get it working, but it's a bit more strenuous to get it installed and running. So we just opted for MolScribe and MolNextar. We installed all these toolkits. We ran all these toolkits on 4 different publications, which actually talk about natural products when they discovered. One of the major journal, as Chandu also mentioned, Journal of Natural Products, Phytochemistry, Molecules, and Phytochemical Analysis. If you see in these graphs that not all tools work well on all the journals equally, and some tools work on certain journals. So for example, in our case, Decima works well on Journal of Natural Products and Phytochemical Analysis, whereas MolScribe and MolNextar works on other journals. On average, still Decima performs well, but sometimes it does not work well on all images presented in the publications. One of the things which for us, the Decima offers is Markov group handling, because we try to embed the Markov groups R1 and R2 notations directly in SMILES and later read them directly into a MOL file. So beyond OCSR, we have to look into text extraction. How the text is represented in the literature, can we mine it in a meaningful way? Yes, we can do it using the language models. If we want to train a language model, let's say we want to extract all the information which Chandu showed in his last slide, can we do that? If we want to do that, we have to probably train a language model. Is there a data set available online to do that? No. So what we in theory did was took random 100 Journal of Natural Products article which introduces a new molecule, and we hand annotated them using an open source toolkit called Docano. We in theory, like Chandu, Jonas, and Victor from our group, we sat together and hand annotated these articles. We later used this data in order to fine tune a GPT-4o model. Why GPT-4o? One of the things which we considered it should be easy to use, and also it should be fast enough and also accurate enough. GPT-4o was the closest which we got. So we are using GPT-4o for now. In future, if a local large language model does better performance, we will switch to that at any given time. So in order to automate this whole thing, what we are doing is we take the PDFs and we use docling from IBM to extract the text into a markdown file. We manually hand annotate them, as I already mentioned, and then we fine tune a large language model. After fine tuning the large language model, if you give a new data, it will create a JSON output as shown here with all the information which we are interested in for Coconut. With all this information, we later built a tool called Markers. Markers stands for Molecular Annotation and Recognition for Curating Unraveled Structures, where we created a platform where the user can upload a PDF, extract the text, extract the annotation from the text, and later extract the chemical structures and use any of these three open OCSR models to get the extracted structure in a machine-readable format. So apart from this information, Markers also can do structure detection. So if you say want to check where the chemical structure extracted comes from, it automatically shows you. And also you could take one chemical structure which got predicted and compare it with other OCSR tools, whether all three does say this is the same structure, they agree or disagree in how much they do an agreement and how valid the results are, and so on and so forth. A short video to demonstrate Markers is being shown here. So a user can upload the PDF. Once the PDF gets uploaded, he can check whether the PDF is already available in Coconut. If it's available, it will show up immediately with how many molecules in Coconut. And once you click extract text, it will use the IBM docling module to extract the text. And then the extract structures will bring in decimal segmentation to segment the structures. Later, one could go through the text annotation. This was annotated using GPT-4o. This happens in behind the scene. Once you're happy with the text annotation, later you can select which structures to convert into machine-readable format and select your desired tool. And if you want, you could also edit the structure immediately in the same display as well. And if you want to compare with other predictions, you can do the comparison. Here you could see whether all three tools agree or not. If you want to get the same exact coordinates, that also could be done. Later, you can select your desired results, get the structure prediction back. And if you want to edit, you can re-edit them. And once it's done, you could also see where the structure comes from. With this information, if you're happy with it, what you could do is you can directly prepare the data for Coconut submission directly from Markers. If you click on prepare for coconut, there will be a form popping up with most of the information entered. If you already have a coconut login, you can log in directly from Marcus and submit this data to Coconut. Apart from printed literature, Marcus can also do hand-drawn chemical structure extraction. So here you could see a few of the chemical structures. You could extract them, and using Decima's hand-drawn model, you could convert them all into machine-readable format. So once these chemical structures are converted, you can either download the data directly from Marcus and use it for your work. So Marcus is already available online. If you visit marcus.decima.ai, the publication got accepted this week in Digital Discovery, and the paper will be available soon. And meanwhile, as Chandu already mentioned, Coconut is already published in NAR, and you could already check out the paper. With that information, I would like to acknowledge my team here in Vienna and the funding organizations and everyone who helped us to build Coconut and Marcus. With that, got questions? We are happy to answer.